All right, ladies and gentlemen, here we go with, whoops, not that fast. Come on, where did my, oh, figures. All right, here we go again. Let's try this now. Now I have my screen set up how I want it. All right, chapter 3.1. We're going to, the goal of this is to understand and apply the concept of vectors to physics and physical problems. And when we're going to deal with vectors, we're going to deal with vectors for the rest of the year. And this chapter is going to be one of the hardest one because we're going to be looking at 2 dimensions. That's going to be a bit more complex. And we're going to look at motion in 2 directions. So in order to understand that, we're going to be playing with vectors. And vectors are basically a value that has a magnitude by the along the arrow, and the head, it gives us the direction, this arrow. And this is all what a vector is. And we're looking at relatives. So when we draw vectors on a piece of paper, we're not going to be exact. We're going to draw relative arrows because it's hard to get them really exact. We don't need to do it for this type of problem. So here are the things we need to talk about. A scalar, anything that has a measurement but no direction. Any measurement, any value that we have, like 50 centimeters. We're talking about something that's 50 centimeters long. We don't know. We don't need to know the direction of it. But if I travel 50 meters to the east, that now is a vector. It has a measurement that has both magnitude and direction. And so what we usually do this is movement of direction, velocity, acceleration, and a couple other things. So anything that can have a direction to it, we're going to be messing with in this chapter, especially velocity and acceleration, and a little bit with direction and distance. Now, the resultant is the vector result of adding 2 or more vectors together, and this is important. We're going to add vectors. So we're not going to multiply, we're just going to add. So now we go with arrows. This length of the arrow indicates the magnitude, and it's called, I'm going to say, the relative magnitude. Because we're not going to have a ruler and have a scale or anything. We just want to say if this is 10 centimeters, fine. If I want to go 20, I kind of increase it that way. Now the direction of the arrow, when we put an arrowhead on it, this is due east or to the right. This is north or up. You get the idea. The arrow is going to tell us in which direction it's going. Now in the text, they represent vectors by bolding the face of the text and the arrow. So basically they make a nice strong arrow. And sometimes you may see in mathematics BE, there's a vector going from B to E. Or BC, we have a vector. And it's an arrow. But we really just put it in bold and we don't worry about it because we're going to be drawing these things. Now, properties of these vectors are going to be interesting because we can take vectors and move them parallel to everybody. And so we're going to move them back and forth and can be parallel to themselves. And vectors can be added in any order. So if we have vector A and vector B, I can put A and B like this, or I could put B then A like this, and the resultant is going to be the same. So that is something we need to put on. No matter how we add the vectors or which ones we add first or last, the cumulative property of vectors, after you add them all together, the resultant is going to be the same no matter in which order we put them in. That's going to be very important. And vectors are subtracted by adding the opposite vector. So if I have A and then B, I want to subtract B, I just flip it and make it go the other way and we want to go head to tail. So first vector, then the second vector, so forth. Or second vector going this way. If I want to subtract, I just flip it and make it go the opposite way. This is what we mean by adding head to tail on vectors. So if you divide or multiply a vector by a scalar, it results in a vector. The direction doesn't change, just the magnitude does. So magnitude changes only. Okay, I want to point out we're not going to be multiplying vectors. That's for another class entirely, or higher level physics. We're not going to do that in this class. So we're going to have a sample problem here. This is and I think you got this as part of sample A, part of the sample set A. We drove 500 to the east and then 1,000 to the north. My vector's a little bit wobbly. We want to know the resultant. We want to know, and I'll change my pen color. And we want to know what this guy is here. We want to know the resultant, both the direction it's going, this angle, because it's his beginning, here's the end. This is our first part, so this is the angle we're looking at, and we want to know what the resultant, and this is going to be 500 meters. So easy. C a squared plus b squared is equal to c squared. Therefore, square root of a squared plus b squared is equal to c. So we can get the hypotenuse first. So we take 500 and make this square it. Where's my square? Plus 1,000 square, and that's going to be 1,250,000. If I take the square root of that, I'm going to get a value of c that's equal to 1118 meters. So my displacement resultant is going to be 1,118 meters. Now this is the displacement, the final displacement. Now what's this angle? So that's going to be inverse tan of the opposite over adjacent. So that's going to be 2, and the inverse tangent, that's going to be an angle of 63 degrees. So 63 degrees is the angle. So my resultant is this way, 63 degrees from east, between north of east, going at 1,118 meters. And that's how we determine the resultant. Thank you, guys.